Good morning, everyone, and I thank Yuvraj Sharma for inviting me today and all of you to host me in your design school at Manav Rachna International Institute of Research and Studies. I'd like to share with you a couple of information about my experience, a very short bio. And let's move on the first slide. I am an architect with a PhD in architecture from the University of Naples Federico II. Currently, I am an independent researcher focused especially on environmental and computational design. I have published scientific articles about parametric design, BIM, and the computational approach to architecture. I was a consultant for the Apple Developer Academy in Naples, and I worked for a iMesh company in Italy for different project tasks. The most famous one, it's more likely, was the Expo Dubai, the main promenade of Expo Dubai 2020. As my latest experience, I worked for Foster and Partners in the UK in London as an environmental design analyst to support the BIM team in carrying out some guidelines and reports based on environmental design assessment. I mean, daylighting analysis, comfort analysis, and so on. Let me say that I try always to be attentive to integrating new technologies in my workflow, for instance. And recently, even AI powered in somehow. I don't know if how many of you already know the Ambrosinus toolkit, but I will talk about it later. And let me also say that I'd like to enhance architectural design this way, especially by developing tools and workflow based on team skills, just because I like to simplify the life of architects and engineers. Let me underline this point, also this point, because in my opinion, nowadays, the integration of computer programming to architectural design, it seems almost a natural fact. But I assure you that until a few years ago, it was not like this. The way our research evolves, or the specialization of our work changes, depends on which topics we are influenced by, and even which people. The first prerequisite for having the greatest possible number of inspiration is to interact with many people and also many operating environments, just to have more possibilities to create new things or combine more information together. All these aspects, generally, we name it combinatorial creativity. It is a particular way to put all these things all together. We have all been students, and I confess that we never stop being a student. But anyway, let's say also this, that the exam is a sort of never-ending story. In my personal case, I was influenced by my engineering studies, and you know that the rigorous approach to calculations and the way of analyzing problems that greatly influenced my subsequent studies in architecture. I don't want to deny that I learned what an algorithm was in engineering course, and for instance by using MATLAB, C++, the programming languages. But beyond the programming languages, it was the logical structure that fascinated me. And let me also say that today we know how to give it a name. About this logical structure. We call this logic computational thinking. Let's move on the next slide. As a student first, and then as a professional, I asked myself so many questions. But the most relevant one, in my opinion, was this. Why the computational approach to architecture and design? And I believe that computational approach can contribute positively to the education and the cultural training of the digital architect. And essentially, there are two reasons. The first, it's about a question of organization of design thinking, because IT and architectural design have a different and scientifically well formalized structure, and this difference becomes the strong element on their meeting ground. Today, and I like do this, call this meeting ground between IT and architectural design computational design, properly computational design. The second one concerns the possibility of expanding the design intention with the aspects that are not just material. Think of bricks, construction elements, pillars, beams, wood. Not only this aspect, but even and also immaterial one. Obviously, this immaterial, in any case, will be representable by data. Water, wind, the effect of water, wind, or the effect about well-being conditions, thermohygrometric conditions, managing solar availability inside a building. Let's move on the next slide. A further justification for promoting the adoption and use of computational design lies, in my opinion, primarily in the strategic and the tactical logic that defines its workflow and its conception. Through this structure, which I call process template, as you can see in this slide, it is somehow possible to define the development of any type of project, whether it's the development of a new tool, or for example a new Grasshopper component, or simply a scientific document, or even a presentation of your project, of your experiment. Let's take for example some meaningful words that characterize this template. In the logical box, for instance, we have abstraction, that is the ability to reason about problems in terms of systems, and therefore the ability to remove detail deemed superfluous for a clear description of the problem itself. But we have also breaking down, that is a valid, especially for thinking about the given problem in terms of components and allowing for a more careful evaluation of them as a part of the whole. Obviously, we have all the process involved in the simplification of the complex system, for instance, and the strategy of generalization is useful in the act of recognition of recurring relational structures within the complex system. We call this structure with the name pattern, for instance. And in somehow this can facilitate the recall and application of previously existing solution schemes. Finally, for instance, just to be very short, we have the assessment, in which there are two interesting and powerful words, in my opinion, that are effectiveness and efficiency. These two words become useful elements for classifying a generic process. While at the end, just to give you an idea, we have techniques, but techniques represent how it is possible to act on a practical level, and so in the application of your workflow. Therefore, there are different types of analysis tool, for instance, or analysis way to manage your data, for example, with precise mathematical procedures, or for example, using different types of programming languages. Why not? Like Python, C#, Java, HTML, and so on. Now, listening these words, the meaning of these words, my subsequent observation is this one. Aren't all these actions already part of the responsibilities and tasks of an architect or an engineer? Maybe. Yes, they are. What does an architect do, for example? Break down the problem in the sub-problems, such as functions, needs, constraints, standards, materials, structures, installation, and so on. It can recognize the patterns that are repeated or that are common to different problems, such as typologies, solutions, geometries, proportions, rules, and so on. Abstract the essential characteristics of the problem and the solution, eliminating superfluous or secondary details, and using models, diagrams, symbols, codes, and so on. It can define an algorithm. Yes, it can. It can do this. It can do this. If an algorithm is a sequence of logical and precise steps to create the solution using tools such as drawing, calculation, rendering, 3D printing, and so on. So, computational thinking, in my opinion, is nothing more than a way of formalizing and making the design process more efficient through the contribution of information technology. Obviously, all these things are possible thanks to the art of coding and scripting, that are two of the most powerful action that an architect or an engineer can do in this our digital era. What does Grasshopper represent in the paradigm shift in the AEC industry? Let's say that computer programming has always represented a way of interacting with machines. Languages such as Lisp, MathScript, Fortran, or like the parameterization associated with the geometric elements were already present in other tools, in other application software like Generative component by Bentley, for instance. Grasshopper has not created the node logic. It was already employed in various industrial sectors, for instance, from the automotive to the filmmaking sector, up to the AEC industry. However, since 2008, Explicit History, The Future Grasshopper by David Rutt and McNeil Associates, has the merit of having definitely cleared programming according to node logic, defining the concept of VPL, Visual Programming Language, in a clear and simplified way. All of these aspects are very closely and linked to the world of makers, fab labs, and 3D printing. I remember the explosion of these movements around 2010-2011 with the MIT Fab Lab, for instance. Now let's move on to the next slide. This slide is, in my opinion, the most important one, because it represents a sort of core aspect of the computational design, or let's say better, the pedagogical aspect of computational design. Let's say that from a cultural and practical point of view, there are lots of studies about the adoption of visual programming language platforms, and many of these studies have been theorized by Professor Robert Aish, one of the greatest experts in the BIM and computational design. For those who don't know him, he is also the father of Dynamo, the VPL version of Grasshopper by Autodesk. So the Aish studies have in a certain sense scientifically justified the benefit conferred in the architecture and design field of integrating data of different nature inside the modeling, design, programming stages. The real paradigm shift conveyed by computational design lies in the ability to deal no longer only with geometric objects, but rather with the information associated and associable to them. In this slide, I share with you the Aish studies. The fourth graph representing somehow how the computational design, how a different approach to the modeling stage can increase the capability of the designer in deeping dive into the given problem. For instance, in the first graph, you know that when a designer models by direct manipulation, he can quickly obtain interesting results for his modeling effort. But if he or she wants to change, refine, or increase the complexity of the model, this process may require an exhaustive amount of additional effort. So that's why a perceptive designer may search for an extra way to overcome these limitations. So in the second graph, when a designer uses associative or parametric modeling, he may need to initially invest more effort in creating the first associative model, maybe than they would with the regular modeling. However, about this investment in design logic makes easier for the designer to change and refine the model compared to the non-associative modeling. So, also in this case, a perceptive designer may search for an extra way to overcome the limitation of associative modeling. So that's why we have the third graph, because in the third graph we have scripting and programming that can require a lot of time and effort without much evidence of the success at first. Once everything works, the complexity of the model and ability to regenerate the model with radically different design logic appear more powerful than what can be achieved with associative modeling. So that's why the computational design or the computational thinking is absorbed completely in the fourth graph, is represented completely in the fourth graph, because the last on the right, because this logic, I mean associative modeling plus scripting and programming, can trigger some changes in the curve slope, not only operationally, but also in the level of cognitive depth of the problem addressed. What I mean? I mean that the computational design, with and through the computational design approach, you can deep dive into the given problem. What does it mean? It means that you have a change in your understanding of the problem. And when you increase your understanding, you get a change in the curve slope. At the bottom of this slide, we have a good recap of all the Aish studies, especially in regarding this fourth graph. And through this 4 point, it's relatively easy define the core aspect of the computational design. For instance, we can we have an explicit identification of variables contained in our workflow. The computational design can easily build a logical dependencies between variables and the construction geometry, often through long chains of relationships within complex flowchart. I'm referring to flowcharts because I have clear in my mind a sort of node logic that comes from visual programming languages. Is quite easily define all the performative rules that can be measured inside our workflow, inside our design strategies, and through the variation and alteration of these variables, factors, and also logical dependencies, it is possible to understand and promote the genesis of further design solution. We can do this as a sort of a teaching exercise. Let's move on the next slide that represent a sort of recap of Aish studies, and in these slides I added at the bottom of this graph an extra observation, because as well as my personal experience, I understood that the computational design helps to experiment with the heuristic part of design. By heuristics, I mean precisely that ability to search and combine the information inside our workflow process and not necessarily find specific solutions, but rather families of solutions. An important engineering lesson that I have learned is this one, that basically it is impossible not to make mistakes, but the important thing is to acquire the ability to know how to manage the error. In this, computational design is extremely powerful weapon that we have in our hands to manage all these aspects, all the complexity that comes up in design challenges, in architectural challenges, in engineering challenges. Next, move on next slide. This is a really provocative slide. I showed this slide during my master thesis, if I remember well. But anyway, even I speak about coding, programming, scripting, everything could be interesting for computational design. I have never forgotten to be an architect. As well, I'd like to use this conceptual slide because in my opinion there is a certain similarity between Filippo Brunelleschi, one of the greatest Italian architects of the Renaissance, who created the Dome of Santa Maria in Fiore in Florence, the most famous cathedral, one of the most famous cathedrals in Italy. And I believe that Filippo Brunelleschi has a certain similarity with the current architects that work in the digital world. Why I'm saying and I'm telling you this? Because above all, for this similarity is to underline the ability that had Filippo Brunelleschi in creating his own tools, even before building the dome. That is, Filippo Brunelleschi had to solve the problem of building cranes and mechanical weight lifting systems, even before being able to build the cathedral. Therefore, he had to invent tools to be able to materialize his project idea. And in my opinion, this is exactly what happens today with information technology and with the programs and programming languages. So let's move on the second provocative slides. Because, well, if you think about the Brunelleschi cranes, the Gaudi's catenaries, or Frey Otto's soap bubbles for his membranes, the use that engineers and architects make of a computer construct and what today is possible to do with the programming languages integrated into the design process is not so dissimilar from these ancient or historical tools. In this brief discussion, I aimed to present some key elements that underpin my vision of computational design in the field of architecture and engineering. All these aspects form the theoretical and the cultural foundation on which this scientific discipline is built and evolves. This short overview begins with the procedural logical aspect and extends the pedagogical implication that computational thinking exercises and promotes to the noble art of creating our own technical tools just to materialize the design ideas, and so, finally, our vision. After this cultural aspect and after all these observations about computational design, I'd like to share with you a couple of examples, my personal examples that comes from my master thesis. I was one of the first students to integrate this parametric approach in environmental design project and use this analysis to reflect effectively the design strategies in some specific area of my master plan, my urban master plan. I always, as I said earlier, to integrate a spark of innovation on each step of my workflow. I mean, even the possibility to integrate some specific analysis about tree species and how to involve these tree species inside my workflow, how to exploit their shadows or shading effect to improve the comfort condition in some specific urban area. But also I found, especially at that time, more or less 10 years ago, the capability to integrate some generative design aspects in my workflow, even involving the Ecotect and the first one of the first version of Galapagos, an evolutionary solver integrated into Grasshopper environment. But another interesting way to introduce some sparkle of innovation, in my opinion, it's also to transfer some rules, some standards inside your design process. In my case, in my study case, for instance, I integrated the behave index, the biotope area factor that comes from some German research, and other standard and rules that comes from Italian standards directly inside my thesis, because one of the most important things in my my idea behind the master thesis, it was the ability to collect everything inside in one unique environment. That in that case, it was Grasshopper, but also Rhinoceros. I mean, always the McNeil and Associate platform. Generally, I like speaking about Grasshopper as a sort of a hub, a sort of a platform where you can, when you have the ability to collect all this information inside a unique process, inside a unique workflow, design workflow, and define within it your strategies and your tactical task, your tactical approach to resolve some architectural challenges. Okay, yeah, also in my PhD thesis works, in my case studies, because at that time I was involved as a PhD student in this collaboration sorry, between Department of Architecture of Naples and Apple Developer Academy. I tried to use also the BIM aspect in this project. I mean, at the Department of Architecture in Naples, I was the first student, if I believe, just to be sure the chronological order of this evolution, of the evolution of this way to approach the design project. I mean, I introduced the computational BIM to define the specific position of these chairs inside the main classroom of the Apple Academy, and I did this process thanks to a very useful project that called flux.io. Now it was a sort of exchanging platform where you can exchange different data across different platform, different software, like in this case Revit and Grasshopper. Nowadays, if I remember well, flux.io is replaced by Speckle, a greatest and really powerful tool that we can use in our workflow, in our design workflow. These are a different image that comes from a sort of infographic that I have elaborated during that time, just to express also the level of satisfaction of the students about the use of main classroom and different labs inside the Apple Academy. Even after, in my working experience that started from iMesh company, I was involved in different projects, especially in doing some environmental analysis, a lot of environmental analysis to improve the capability of these membrane systems. I want to add just a couple of information about iMesh, because it was a great experience, and nowadays iMesh is one of the main partners of my LA consultancy services. It is a company that produces panels made up of filaments, of fiberglass, carbon, basalt, and other mineral materials, which are subjected to resin coating process to increase their performance characteristics. So, to improve this characteristic and to manage at top level all these features inside the architectural project that involves iMesh, I elaborated different scripts, different algorithms to improve this application, or the application of iMesh in this project. especially for managing the thermal condition, thermohygrometric conditions, the comfort condition under these membranes. Anyway, let's also say that I was involved also in some PhD thesis made in partnership with iMesh and a variety of universities from Polytechnic of Milan, University of Camerino, and other German university. Even during my experience in Foster and Partners, I understood how was important to define a sort of filtering system within the computational design workflow. Why I'm telling you this? Because sometimes to run daylighting analysis or other simulation, these represent a very consuming time task, and one of the most useful way that you can apply computational thinking is in reducing this kind of limitation. Sometimes this daylighting analysis took more or less 6 hours to run, and within my experience and my curiosity to reduce this consuming task, I elaborated different filtering strategies to speed up this process. And also realize some helpful script for my colleagues from my team. For instance, even the capability of these scripts in recognize the horizontal surface that can be destined to the photovoltaic system, for instance, could be an interesting task for a computational design. In my opinion, before to be a problem solver, because namely computational design is a sort of a problem solver, but in my opinion, before to be a problem solver, you need to be a problem maker, understand very well and deep dive the given problem. By this way, you can find new solution, let's say find new solution, and also increase the capability of a team in solving architectural challenges. So this is just a very short example, a very simple way to integrate computational design in architectural and engineering fields. Even the realization of some specific cluster or some specific tools in generating the Louver system, the Louver configuration, and changing this configuration very quickly to assess the daylighting behavior of a building or inside rooms. This in particular was one of my latest elaboration at Foster and Partners, I believe, because this task involved the capability, the possibility to vary, to edit the windows wall ratio over a curved walls. Essentially, this was a process that my colleagues did in manually manner, but from my vision, within a couple of days, I elaborated some specific scripts to accelerate this task, to improve, and left my colleagues to be more focused on some other specific tasks. Finally, so we have nowadays the advent of the artificial intelligence. I was captured by these tools, this new way to think about the architecture and the challenges of the architectural fields. I elaborated and coded this plugin for Grasshopper named Ambrosinus Toolkit more or less 2 years ago. I had a sort of hybrid approach because some components has been developed in C# language. That is the most quick way to share your project among different platform. also between Food for Rhino, for instance, and the Rhino Package Manager. And other tools, other components, let's say, has been developed in Python Sharp, in Python languages, sorry. There are a lot of Python libraries that are dedicated to artificial intelligence. And also for this project, I was fascinated especially to study the way how architects and designers can integrate these features, these AI features, directly inside Grasshopper and directly inside their own workflow to improve their creativity. Let's move on the final part. Really, this is the final part of this quick speech, of this sharing moment with you about my personal experience and what I think about the computational design world. I believe that these following words, these following observation from my side could represent in somehow a sort of a computational design manifesto. And I hope that you could find this observation helpful for your study, for your growth. Computational design is not just an advanced design tool. It represents a true revolution in how we conceive and organize work in architecture and engineering firms. For too long, our sector has normalized a toxic culture based on exploitation, where unpaid overtime hours and the sacrifice of a personal life are considered prerequisites for professional success. This mentality is not only ethically wrong, but also deeply counterproductive. Computational design offers us the opportunity to break down this obsolete paradigm. Through the automation of repetitive processes, workflow optimization, and parametric project management, we can finally free professionals from tasks that traditionally required endless hours of manual work. But transformation cannot be solely technological. It requires a deep rethinking of leadership. An effective manager must know how to recognize and value uniqueness of each team member. There is no universal approach. Each professional has their own way of expressing talent, their specific competencies, and their own key to reading the project. The true ability of a leader lies in knowing how to tune these different instruments into an harmonic design symphony. When a team consistently finds itself working beyond established hours, we are not looking at a sign of dedication, but a clear symptom of managerial inefficiency. It means that the manager has not been able to foresee the critical issue of the process, or has not deeply understood the technical complexity of each phase, or has simply distributed workloads superficially, treating each resource as an interchangeable instead of valorizing their specific competencies. Computational design thus becomes not just a design tool, but an ally in intelligent management of time and human resources. It allows us to precisely map processes, anticipate critical issues, and distribute work in a targeted and efficient manner. This means that a young architect or engineer will no longer have to sacrifice their evenings and weekends to compensate for inadequate planning. It's a time to recognize that true innovation does not come from exhausted and demotivated teams, but from professionals who have the time to think, experiment, to rest, and live balanced life. Computational design, combined with the enlightened and conscious leadership, allows us to demonstrate that professional excellence and respect for working hours are not conflicting objectives, but fundamental prerequisites for the sustainable future of our profession. It is important to discuss a crucial aspect of the workplace for two reasons, in my opinion. Firstly, architects and engineers are believed to be among the last intellectuals within the technocratization of the AC industry, capable of offering reflection, observation, and direction beyond productivity. Secondly, with the rise of artificial intelligence, some observations may become obscured or forgotten, while others may be validated. In this period of cultural uncertainty, it is essential to remember the human element. Although there is no definitive answer, I don't have a definitive answer. Sharing a vision or experience related to design and architectural or engineering challenges, which in some way contribute to making man human and to binding him inextricably to his work effort, namely curiosity and passion. Passion and curiosity are two of the most powerful forces driving human progress and personal enrichment. Passion is that inner flame that pushes us beyond our limits, that makes us rise at dawn to pursue our dreams, and transforms work into vocation. It's that inexhaustible energy that allows us to overcome obstacles and rise after every fall. When we are passionate, time flows differently. Difficulties become stimulating challenges, and every small progress fills us with joy. Curiosity, on the other hand, is the spark that ignites new ideas and discoveries. It's that inner voice that whispers, "What if?" or "Why?" pushing us to explore the unknown. Curiosity keeps us young in spirit, allows us to see the world with fresh eyes, and find unexpected connections between seemingly distant ideas. It's the engine of innovation, the seed from which the greatest discoveries germinate. When passion and curiosity merge, they create an extraordinary synergy. Passion provides the determination and energy to pursue the questions raised by curiosity, while curiosity continuously fuels passion with new challenges and perspectives. Together, these qualities allows us to grow continuously, reinvent ourselves, and leave a significant mark in our room, in our neighborhood, in our company, or for the most lucky in the world. There is no age limit for passion and curiosity. They are gifts that we can cultivate throughout our lives, transforming each day into an opportunity for discovery and every challenge into an occasion for growth. They are the salt of life, what makes every experience richer and more meaningful, what drives us to exceed our limits and achieve the impossible. So I would like to conclude this speech and this sharing moment with you with these words: stay curious, stay human, and as an Italian I tell you, have a passion. So thank you so much for watching this video message, for listening to me, and I just have to thank you for this sharing moment, and I wish you a wonderful start to your studies. Bye bye, and I hope to keep in touch with you. Say hello. Bye.